Hello, everyone, and welcome to our discussion for today. In this discussion, we're going to talk about the sixth trigonometric ratio, which is one of the important lessons in trigonometry subject. So without further ado, let's now begin. Suppose we have two similar right triangles, and these right triangles are in 45, 45, 90 right triangle, or 45 degrees, 45 degrees, 90 degrees right triangle. So we have this one, the first triangle. So hold on. So this is 45 degrees, 90 degree. This is also 45 degrees. Okay, but I prefer not to write it. You will know later on why I decided not to label 45 degrees here. So yeah, the side lengths are 1 square root of 2 all over 2 and square root of 2 all over 2. Then we have another right triangle here, which is this one. Much bigger than the first one. So this one is we will have 4. This is 2 square root of 2 and 2 square root of 2. So the same angles. So how would you know if two shapes are similar to each other? Well, first and foremost, they have the same interior angles. Basically, the angles here. So if we have 45 degrees here, then its corresponding angle is also 45 degrees, which is they're the same. If we have right angle here, then the corresponding angle is also a right angle. So it's true because this is also right angle. So that's good. And here, whatever the angle will be here is also gonna be the angle here. And if all of the interior angles are the same as the interior angles that is corresponding to these angles, then they are similar. The second thing that uh, the second way on how would you know if they are similar is by their common ratio. Okay. So let's just say I will have a shape here. Right. Let me draw a shape. I have a rectangle. Okay. Now that I copy and paste this, okay, I still have a rectangle. No changes at all. Right? Now imagine that I will shrink this one. Oh no, sorry, shrink. I'll shrink this one. You see, the way how I shrink it and increase, you see, it's at the same rate, you know. The way how the rate of this side decreases is the same rate how this horizontal side decreases. So I never decrease it like for example, like this, like like that. Oh wait, no. I never decrease it like this or like that, then like that. No, no, no. Right? I never did that. I rather decrease it in all, I decrease all sides in the same rate. So it's like this. So you see, these two rectangles are similar to each other. Now, what we're going to do here is we're going to relate their ratios. So in the right triangle, we have two parts, right? The length and the width. Okay? Let this be the width and let this be the length. And let's get the ratio. The ratio of length to width. Okay? Length to width. So let's just say this is 2, 4, 4, 2. And the other one that would be 1, 2, 2, 1. Let's get the ratio of the width and length here. So the width here is 4 and the width here is 2. So here on the other rectangle, the length here is 2 and the width is 1. Now let's have a proportion. Proportion, if in case you don't know, it's the equality of ratio. So we will equate these two because if they are similar to each other, then they have a common ratio. So therefore, we will have a proportion. So 4 is to 2 is equal to 2 is to 1. So this one, we can rewrite it in a fraction form. So we will have 4 all over 2 and 2 all over 1. 4 divided by 2 is 2 and 2 divided by 1 is 2. So they're the same. So that is their common ratio. Now, let's relate it here in this, in these two right triangles that are similar to each other. So here, in terms of their similarities, so we're going to relate their parts. So you see, in a right triangle, before I actually never mentioned the specific labels or representation of a right triangle. All right? Because so far, what we know is that in a right triangle, this one, the side here, right, the side here is the longest side, and these two are the legs. But you see, they have their own names. Okay? The longest side is what you call as the hypotenuse. Okay? Hypotenuse. Okay, it's hypotenuse. Then here we have the legs. Okay, we have the legs here. Now here in, wait, sorry. In these legs, they have their own labels. And they can either be opposites or adjacent. How would you know if a side of a right triangle is opposites and the other is the adjacent? It depends on the given angle. That angle will be your acute angle. So, for example, I have an angle here. This is an acute angle, by the way. An acute angle is basically an angle that is greater than 0 degrees but less than 90 degrees. So it could be 60 degrees, 35 degrees, so on and so forth. So if we have an acute angle here, so what will be the result? So here, if the side has an angle beside it, like this one, the angle is beside with this side, that side will be your adjacent. So this is your adjacent. Now, how about the side that has no angle beside it, or no, rather, let's just say it's not beside with this angle, which is this one, okay? This side is not beside with that angle. So that will be your non-adjacent side, or in other words, the opposite side, okay? So if the side is beside with an angle, that's the adjacent. If the side is it's not beside with that angle, then it's opposite. The main reason why it's called adjacent, because it is adjacent to the angle, or it's beside with the angle. All right. Now, how about if I have an angle here? If I have an angle here. So what will happen if I have an angle here? So the position here is reversed. Okay. This side will no longer be adjacent because it's not adjacent to that angle. So this is opposite. And that side, the smaller side here, that will be the adjacent because it is beside with that angle. So now, what if there are two? Because right earlier, I have 45 degrees here, right? So that means we also have 45 degrees here if they are similar to each other. So that means I have two angles here. Okay, let this be angle 1 and let this be angle 2. So I have a total of two angles. So which one is the adjacent? Which one is the opposite? So the answer is it depends on what angle you're referring to. Okay, so for example, if you're referring to the angle 1, so what would be your opposite and what would be your adjacent? So if you're referring to angle 1, therefore, the side here is your adjacent. Okay? This is your adjacent. Then, the side that is not adjacent or beside with angle 1, that would be the opposite. Okay? Now, what if it's you're referring to angle 2? Okay, like you wanted to base the angle, but it's angle 2. So in here, since the angle 2 is here, therefore this side is not opposite. Rather, this is your what? Adjacent. Wait, I can't. Yeah, this is your adjacent. And this one is your opposite. So far, so good. Okay, so that's it. Now, let's go back here. All right, let's go back here. Suppose we only have one given angle, one given adjacent side, which is adjacent to the base. So we don't have an angle here on the top. Now, let's find the parts. This one, you already know this is your hypotenuse or HYP in short. This one, since the side is adjacent to 45 degrees, that would be your adjacent. And this one, a side that is not adjacent to 45 degrees, is your opposite side. Okay? So now what are we going to do? Now, we will find the ratio. Unlike for the rectangles, right, they have two dimensions, the length and the width. Now here, we have hypotenuse, opposite, and adjacent. So we have three dimension actually. But don't worry, it's not that hard. What we're going to do is we will get the ratio. Let's get only three ratio. First, let's start with the ratio of the opposites to hypotenuse. Okay, opposite to hypotenuse. So let's start with this one. Let's get the ratio of the opposite to hypotenuse. The opposite in this triangle is square root of 2 all over 2. Now, the hypotenuse is 1. And this one, we can rewrite this as square root of 2 all over 2 all over 1. So the answer here is square root of 2 all over 2. Okay? Now, the same thing here, okay, on the right, on the second triangle, much better. On the second triangle, the opposite is 2 square root of 2, right? And the hypotenuse here is 4. So therefore, you have 2 square root of 2 all over 4. 2 and 4 are both divisible by 2. So 2 divided by 2 is 1, and 4 divided by 2 is 2. So you have square root of 2 all over 2. See? They have a common ratio. If it's about the ratio of opposite to hypotenuse. All right? Now we have another one actually. All right? We have, wait, let me erase this one because I'm going to, wait, you know what? Let me just select them. Now, how about if we talk about adjacent to hypotenuse? Right, adjacent to hypotenuse. So this one, we're going to get adjacent and the hypotenuse. So in this triangle, on the first one, your adjacent is the same as the opposite, square root of 2 all over 2. Then the hypotenuse is 1. Now you do it in a fractional form. The answer is square root of 2 all over 2. Now, for the second triangle, we will do the same thing. The adjacent is 2 square root of 2, okay, which is the same as the opposite. So we have 2 square root of 2 is 2. The hypotenuse is 4. Now this is the same as 2 square root of 2 all over 4. So 2, 4, we will have 1, we will have 2, so we will have square root of 2. See, they are the same. Okay? Now, last but not the least, I would like to have the ratio of opposites to adjacent. Okay, opposite to adjacent. How about that? So let me erase this one and this one. So the opposite and adjacent in this first triangle. So we have that opposite square root of 2 all over 2, and the adjacent is also square root of 2 all over 2. Now, if you're going to do it in a fractional form, it would look like this one. Square root of 2 all over 2 all over square root of 2 all over 2. So both sides of the fraction are the same. So it will result to 1. Now we will do the same thing on the second right triangle here. So we have the opposite to square root of 2 and the adjacent to square root of 2. So do it in a fractional form, 2 square root of 2 all over 2 square root of 2. Both sides are the same. The answer is 1. See? They are the same. So you see, these two right triangles are similar. First, because they have the same interior angles, which I already explained that to you earlier. Then another one is because they have common ratio in all sides. So now, there's actually another way. Okay? Instead of just doing this ratio thing, there's actually another way. All right? And that would be the application of trigonometric function. Okay? So we have opposite to hypotenuse, right? And you want to get the common ratio of the two. So here, the ratio of opposite to hypotenuse is just the same as sine theta. Wait, hold on. It's just the same as sine theta. This word sin, it's pronounced as sine. Okay, sine. Okay? So here, you see we have this theta here. So in this function, your input is the angle. So we have 45 degrees here. So now I suggest you should get your calculator. Pause this video and get a calculator. All right? I'll wait for you. Okay, so let's get sine 45 degrees. So sine 45 degrees. Okay. If you're going to get the value here, it is exactly square root of 2 all over 2, which is the same answer we got in getting the ratio of opposite and hypotenuse. Okay? So we can apply sine 45 degrees here and sine 45 degrees here because the answer is still square root of 2 all over 2. It doesn't change. Now, how about for the ratio of adjacent to hypotenuse, which is this one. So this one, if we have sine, then we have cosine. Right, cosine theta. By the way, wait. Right? Hold on. Let me just plug in my charger because let's just say I'm in a low battery mode. Okay, so yeah, there we go. Okay, so let's go. So cosine theta. So the way how you pronounce the word cos, I mean, the way how you will uh, say this word cos is actually cosine, which is the complement of sine. Okay, so here, all you need, the same thing is the angle. So we have an angle of 45 degrees. Oh, now let's calculate. What's cosine 45 degrees? It is actually square root of 2 all over 2. All right. Now, how about for the ratio of opposite to adjacent? How about that one? Oh, wait. Let me put up there. So this one is just the same as tangent theta. This tan is short for tangent. Have you ever heard this word? Tangent. Tangent line, and so on and so forth. You know that. But yeah, it's short word for tangent. So tan theta is basically tangent theta. So here, let's try to substitute the angle 45 degrees. So tangent of 45 degrees, what will be the result? So here, tangent 45 degrees is 1. That's it. Okay. So here, as you can see, we have sine theta is equal to the ratio of opposite to hypotenuse. Cosine theta is equal to the ratio of adjacent to hypotenuse. And we have tangent theta is equal to the ratio of opposite to adjacent. These are some of the trigonometric ratio. These three are trigonometric ratios. All right. So let me, Let me erase everything here and let me rewrite these three trigonometric ratios. So for sine theta, we have the opposite all over hypotenuse. Okay. Next is we have cosine theta, which is adjacent all over hypotenuse. By the way, it is still the same as the ratio we have. This is the same as the ratio of adjacent to hypotenuse, or adjacent is to hypotenuse. But I make it into a fractional form. Okay. So next is we have tangent theta, which is opposite all over hypotenuse. This is actually the three most basic trigonometric ratios. So right, there are 6. These three are the basics. And these three are sine theta, cosine theta, and tangent theta. These three are the basics. So, what are we going to do here? So here, what do you call this one? We're going to introduce. Oh wait. No. Forgive me. This is adjacent. Okay, it's not hypotenuse. It's adjacent. It's adjacent. Okay, sorry, guys. Anyways, let's go. So what we're going to do here is we will find the other three trigonometric ratios. The other three are just basically the reciprocals of each basic trigonometric ratios. Like for sine here, sine theta, we have a reciprocal of it, which is the cosecant theta or CSC. CSC theta. Okay? So this is cosecant. So cosecant. Cosecant. Okay? It is the reciprocal of sine. So this is 1 all over sine theta, which is hypotenuse all over the opposite. So you see, for the sine, it's opposite all over hypotenuse. This one is what? Hypotenuse all over opposite. Now you see that? Now next, we have the reciprocal for the secant theta, which is this one. Okay? I mean, the reciprocal of cosine theta is secant theta. So secant theta. This one, okay, right? We have cosecant theta and we have secant theta. These two are complement to each other. Okay? So for secant theta, this is actually a reciprocal of cos. Oh, wait. Yeah. No. Cosine theta is a. Wait. Let me rephrase that. Let's just say that the reciprocal of cosine theta is secant theta. Much better. Okay? The reciprocal of cosine theta is secant theta. Okay? So this one, which is the same as adjacent all over hypotenuse. And lastly, we have tangent theta. The reciprocal of tangent theta is cotangent theta. This one is actually the complement of tangent theta. That's why it's called cotangent. Okay? Cotangent. All right? Wait, hold on. Am I decimal? All right, good. So with that, once again, it is complement to the tangent theta. So it's 1 all over tangent theta, which is the same as adjacent all over the opposites. Okay. So these are the 6 trigonometric ratios. Actually, there are more than 6. Yeah, there are actually more than 6. That would be advanced. Like that would be in a future discussion, right? But here, at least you knew that this is actually the 6 trigonometric ratios, or in other words, the basic ones, the basic trigonometric ratio. But yeah, among all the, wait, but yeah, in these 6 trigonometric ratio, these 3 are the most basic. Okay? These 3 are the most basic trigonometric ratio. So before you know cosecant, secant, cotangent, you need to know this one. So where do they come from though? You know, because this is a trigonometric function, right? So where do they come from? So we will discuss that in the future, right? So see you soon.